So this is a representation of what you see in the lab manual. It's a smoothly varying analog signal, and we want to digitize it. Now let's say that we have a 2-bit analog to digital converter. I'll call it an ADC module from now on. If it's only got 2 bits, that means it only can attain 4 values. 2 raised to the power of 2 for 2-bit equals 4, and these are the 4 values it can take on: 0, 0, 0, 1, 1, 0, and 1, 1. We're going to use these 4 values essentially as labels. Let me explain what I mean. When you're doing an analog to digital conversion, what you do is at a certain time, you sample the signal, and then you compare it to a reference voltage. Now on our breadboards, our reference voltage is 5 volts. That's our maximum. But this could be any value. If we've got these 4 values that the ADC module can attain, that means that we can split our reference voltage into 4 bins, that is, 4 ranges of voltage. So this is Vref, and we just split it up into 4 equal parts. The first bin would be from 0 volts to 1/4 of the reference voltage. The next bin would be from 1/4 to 1/2 the reference voltage. The next would be from 1/2 to 3/4, and the last would be from 3/4 up to the full reference voltage. What the ADC module does is it takes the voltage at the time you specified, and it figures out which bin it falls into. So right here at T1, the voltage has just crept into the second bin. And what the ADC module would then remember is that the voltage fell into bin 01, and that's all it would remember. It can only do this once at a time, so if you want to preserve the whole shape of this wave, you would have to sample the voltage at various times in order to capture that, and then maybe write your values into an array. So going through this, at T0, you would tell the ADC module, sample the voltage, tell me what bin it falls into, and it would say, okay, it falls into bin 00, the lowest one. At T1, you would sample it again, and say, what bin does the voltage fall into? The ADC would return a value of 01. At T2, it would return a value of 11, because we're up in this top bin now. At T3, we've actually maxed out, we've gone over our reference voltage. The ADC module will still remember this as being in bin 11, the highest bin, even though it went over. At T4, it's in this third bin, so it would return a value of 10, and at T5, it's still in bin 10. So like I said, you would have to take care of remembering all this information, maybe writing it into an array. So let me show you what information has actually been preserved. So over here is our best reconstruction of what we had over here. So at T0, the ADC module told us that the voltage was in bin 0, and that's all we know. So we draw a voltage right down the center of that bin from T0 to T1. That's the best we can do. That's all we know about the original signal. At T1, we know that the ADC module returned a value of 01. So again, we draw a line straight down the middle of the bin from T1 to T2. At T2, we know that the analog to digital converter said the voltage was in bin 11, so we draw the line straight across, and for the next one it also does. So we just go flat across for 2 time intervals. At T4, we know that it fell into bin 3, that is bin 10, and it stayed there for 2 time intervals. So as you can see, this is not a great representation of the actual shape of the wave. It looks pretty pixelated. We've lost a lot of information. So how could we do better? Well, we could have more bins, for example. So say we had a 3-bit ADC module, so 2 raised to the power of 3 gives us 8. So that would double the number of bins we have here. So let me show you what that looks like now. So here you can see that we've got 8 bins, and we've just subdivided the reference voltage into 8 equal-sized voltage ranges, or bins. And over here, we can see that the preserved signal is better. It's still not great, but for example, we can tell that there was an actual voltage difference between these 2 times. So it wasn't just flat all the way across. The reason why it's better, but not necessarily great, is that there's more than just the number of bins at work here. There's also the sampling rate. So if we doubled our sampling rate, we should again be able to get a better transcription of the original signal's shape. So let me show you what that looks like now. So again, here we've got a better representation of what we saw here. So more bins and a higher sampling rate gives you a better transcription of the signal's original shape. The thing to take away is that if your bin size and your time intervals are small relative to how fast the signal is changing, then you should be able to capture a really great transcription of the signal. There are physical limitations to that, however. Your chip doesn't have infinite bits, so it can't give you infinite bins, and there is a limit to how fast it can take a voltage and convert it into a digital value. So now we come back to the manual just so I can explain how what I've been talking about relates to what's written here. So here they're going over this same hypothetical 2-bit ADC module and noting that you can only get 4 values with a 2-bit ADC module, therefore you can only split your reference voltage into 4 equal-sized bins. Scrolling down, they note that our chip actually has a 10-bit ADC module, so that means we can have 2 to the power of 10 equals 1024 bins. So that's a lot better than 4 bins. Down here they start talking about the limitations on what your sampling rate can be. So let me scroll down just a touch to that. Here they note that there's actually 2 steps to how the ADC module grabs a voltage and then turns it into a digital signal. To grab the voltage, it's got a capacitor-resistor combination with a small time constant tau, and its capture time for getting a signal is about 5 times tau. So you don't want your voltage to vary significantly over that sort of a time scale. But just getting the voltage is not enough. Then it has to actually sort it into a bin. So that's what these next 2 paragraphs are about. Here they define how big the bin size is, so what voltage range it spans. So Vref plus is your highest voltage that you can access. Vref minus is the lowest voltage you can access. So on our breadboards, that's 5 volts to ground. Then they divide it by the number of bins, and that's just 2 raised to the power of the number of bits you've got. So again, this is the size of the bin, Vref plus minus Vref minus divided by 2 to the n. Down here, they're talking about something called the method of successive approximations. So the fastest way to figure out where a number falls in some range of numbers is to first take that range, split it in half, and then test whether your value is bigger or smaller than that midpoint, the center of the range. If it is, then you know your value falls into the upper half of the range, and you would consider the upper half of the range to be a new range. And again, split it in half, and then test whether your value is bigger or smaller than the midpoint of that new range. So this diagram over here explains how that works. So first you start by defining a comparison voltage, Vc, and you set that equal to 1/2 of Vref, so 1/2 of your total range of voltages. And then in this diamond here, they test whether the input voltage is bigger or smaller than the comparison voltage. If, for example, it's bigger, then you'd come over here, and they set a new comparison voltage, again to the midpoint of the new range, which is the upper half of the original range. And again, down here in the diamond, they test, is the input voltage bigger or smaller than this new comparison voltage? And if it's bigger, they say that that voltage fell into bin 1,1. If it's smaller, then they say it fell into bin 1,0. One thing that's kind of interesting to note is every single time you make one of these decisions in the diamonds, you're setting the largest bit. So for example, if you determined that the input voltage was smaller than Vc up here, that would set the largest bit down here equal to 0. So both of these are 0. When you make the next decision, you then assign a value to the next largest bit. And for a 2-bit timer like this, that's all we've got, just the 2 bits. With a 10-bit timer, however, you'd keep making decisions, working your way through a chain, and eventually you would assign values to all 10 bits, but you would do it from the largest bit to the smallest bit in order. So here they're discussing how you take the data that we actually preserved, which is essentially just the bin labels, and turn it back into an approximate voltage. Because we don't remember what the exact voltage was, we only know what bin it fell into. So first thing to notice is that this quantity right here is the size of the bin. So Vref plus minus Vref minus divided by 2 to the n is the size of one bin. Over here, what's this ADC value? Well, that's just the bin label. So this digital value that we preserved, 0, 1, 2, and 3 in the case of a 2-bit ADC module. So you would take that number and you put it down here for ADC value. And why are they adding 1/2 to it? Well, you remember in that graph that I was drawing, when I was trying to show what data we'd actually preserved of the original signal, I always drew the voltage as being right down the center of the bin. And again, that's because I don't know what the voltage originally was, I only know what bin it fell into. So it's a very practical approximation to just assume that it went right down the center of the bin. So if, for example, your ADC value here was 0, 0, and you put that here, the 1/2 just moves you up to the center of the bin. So you put your digital value here, you add 1/2 to go up to the center of the bin, and then you multiply by the size of the bin, the voltage range that it spans, in order to turn this into a voltage. If your Vref minus is not 0 volts, then it's very important that you add this as well. You can work out yourself that you would need to add this in order to get the right value. So everything here in the curly braces is our best guess for what the voltage was, based on the digital value that was preserved for us. Over here, this is the uncertainty on that value, and again, you'll notice that here is the size of the bin. Vref plus minus Vref minus divided by the number of bins. So they're saying that the uncertainty is just plus or minus 1/2 the size of one bin, which makes sense given that we assume the voltage ran right along the center of the bin. Down here, they're just noting that the chip is better at handling integers than float numbers. So if, for example, when you want to display your voltages on an LCD screen, it might be better to work in millivolts rather than volts, because then you don't have to worry about any decimal points.